Okay, so well, so given that there was no notes, this is a real quiz. So how would you estimate, or like how would you get get this distribution mu of x?
We have only the value that value function.
Sorry, can you
We
repeat?
have only the value function for the state. Based on that, we what are the
No, but this is actually the process to learn your value function, right? So you don't have your value functions yet.
you can parameterize that one.
No.
Run a sample episode.
Sorry, what?
Run a sample episode to see what state is.
So based on the sample episodes, okay. Any other answers?
Based on frequency.
There are a few answers in the chat. So one is how many times the state is visited. I think the visitation frequency, and or deduce it from the problem, or learn along with the values, as someone said. Okay. Okay. So if you think about why we introduced mu, it is because we wanted to just make sure that like we estimate the values of states that we care about, right? Now, what are these states that we care about? Normally, we care about most frequently visited states, okay? So, or in other words, like if you have a count of how many times you would visit a state, then that could be a good mu of s, okay? Now, it is also very difficult to get this count for all possible states. So the simplest approximation is what she mentioned, which is basically you do that, you learn through interactions, okay? So when you're interacting, every state that you visit, you're going to update, okay? So we have this mu of x theoretically, but in practice, like we will only do updates for states that we are seeing. So every time you see a state, you make an update. Now, if you see a state more often, you're going to update that state's value more often. If you see a state very less often, then you're going to not make an update for that state like that often. Is it clear? So now this term, right? So this is the means, this is the squared error, mean squared error, okay? So often when we want to report how good is the estimate, we will take square root of this, okay? Because square root of this is going to give you some value in the same scale as the value function, and like that is going to tell you like how much your estimates are deviating. Is that clear? Now, when you're training on policy, which is what we will focus on today, okay? So we are going to talk about off policy methods next week. So when you're training on policy, then the simplest strategy for mu of s is like what she mentioned, which is basically like whatever you are experiencing, you update because you are experiencing from the policy that you care about, right? Now this gets a little bit trickier, like when you are an off policy setting, okay? We'll talk about it later. But for now, we will continue with like prediction, first prediction with on policy, then control with on policy, okay? Now, first of all, is this a right objective for my value function approximator? So what is our ultimate goal? Is our ultimate goal to accurately estimate the values of the state?
Maximizing the reward.
Not really. Maximizing the reward, but how would you do that? By finding the optimal policy, right? Like, so our goal is really to find the optimal policy, and the value functions are just one mean towards it, right? Like, so now this is a little bit of concern that you should keep in mind, that the value functions are already like one approach to achieve your final goal. Now you are approximating this further by considering this B objective, okay? Now, it is not clear whether this particular mean square error is the right objective for my value function approximation, right? So like, for example, like a better, like what could be a better approximation objective, right? Like, so ideally what we want is like, we want a function approximator which will estimate values in such a way that it helps me to find the optimal policy, right? Now that connection is missing here. Like, so we don't have any control over the second step. Like, so we are only talking about estimating the value functions here, okay? So, however, like one can think about function approximators, which directly tries to approximate this final objective, which is the objective of finding explicit, like finding like optimal policies, okay? So we are going to talk about such class of function approximators in a couple of weeks, okay? So that is going to be a completely new way of solving reinforcement learning than all these value-based methods that we have seen so far, okay? So like just as a quick note that we are going to talk about this later, like so there is another class of function approximators which we are going to call as policy gradient methods, okay, where the objective is going to be directly approximating the policy that we care about instead of approximating the value function, okay? So, but that is for future. Like, so for now, even though we are not sure if approximating value function is the ideal thing to do, we are going to see how to do that efficiently, okay? Now, our goal is to find some W star which has lowest possible VE of W, right? Like, so it's basically arg min of W, right? Now, so this W star is the global optimum for this error function, okay? So for this particular error function, the global optimum is given by W star. So when I say something is a global optimum, it just means that the error of that particular weights is going to be always less than or equal to VE of W for all possible W. Okay. Now, for the class of simple linear models that we are considering today, we can actually reach this global minimum or global optimum. Okay. So, however, we are also going to discuss nonlinear function approximators next week. Okay, where there is no guarantee that you're going to find this global minimum, and you would often reach a local optimum. Okay, this is global optimum. You would often reach a local optimum, which is basically VE of W star is less than or equal to VE of W, but only in the neighborhood. Okay, so for all W in some neighborhood of W star. Okay, now imagine you have a linear model, then this particular error function, right? Like it would look something like this. And this is going to be the minimum error, and the W star is basically the configuration corresponding to this minimum error. But when you have non-linear function approximators, okay, your error function is going to look a little bit complex. It might look something like this, okay, which means there are many minimums. So this, I think, is your global optimum, the lowest possible error, but you might converge to either this or this, which are local optimum. Okay, question?
It's an objective function.
Yeah.
I'm not sure if we know V pi. Are you going to replace it with something?
Sorry, what?
Do we know V pi of S?
Okay, well, that's a good question. So first, like, we don't know what is the true value of the true V pi of S, right? Like, so then, what are we regressing for? We will come to that. So that's what I'm going to come to in like few minutes. Okay, so of course we don't have access to V pi of S. Like, so this V bar that you are seeing here is like an oracle. Like if you have access to V original value function, then you can compute how good is an algorithm using this. But in reality, when you want to learn, you're going to have an estimate. So that estimate is going to come from which algorithm you're going to use. If you're using Monte Carlo, you will substitute this with GT. If you're using TD, you're going to substitute with this with RT plus 1 plus gamma times V of ST. So we will talk about that very soon. Any other questions? Okay. So, okay, I think now we are ready to talk about prediction first, then control, okay, as usual. So we're going to do on policy prediction with approximation. Okay, now the way in which we are going to do this is by using stochastic gradient descent. Okay, so we have an objective and we want to achieve that objective. We are going to take gradient with respect to this objective and move towards the direction which is going to help me reduce the objective. Okay, so we're going to do stochastic gradient descent. Okay, now the parameters of our function approximator is given by W1, W2 to WD. Okay, this is my parameter vector. Now the value function approximator is given by W transpose X of S. Okay, now this function that you're seeing here, right, is actually a differentiable function of W, right? So it's just a simple linear function. So what we are going to do is we are going to start with some W0, some initial weight, and we are going to compute the loss with respect to this function approximator. Then we are going to take the gradients. We are going to update this weight based on the gradient, and we get a new weight, W1. Okay. Then we do updates one by one, like we are going to get new weights, and eventually this weight will converge to one particular weight. Yeah.
Yeah, for linear model, I thought we had like a direct formula. So we're doing stochastic gradient.
Yes. Okay, so for linear models, we can come up with a direct formula. We are going to do that. Like, but first we will start with stochastic gradient descent. It's because we are going to see some cases where, like, well, it is just easier for us to like generalize to the future nonlinear models. Okay, so we will start with stochastic gradient descent, and then like we will talk about how to do this in an even more efficient way by exploiting the fact that this is a linear model. Okay, now in each time step, we are going to observe a new example, right? Like, so the example is basically given some state. What is the target? The target is V pi of st, right? Now, I still haven't answered like how to get this V pi of st, right? Like as he pointed out, like, so we don't have access to V pi of st, but for the moment, let us say V pi of s, we have access to V pi of st. So then my stochastic gradient descent update is going to look something like this. So Wt plus 1 is equal to Wt minus 1 over 2 alpha dou by dou W of V pi of st minus V of st given Wt. Is that clear? So I'm doing sample, like I'm okay, first of all, I'm approximating the value error by just this one sample, right? Like, so if you think about VE bar is summation over all possible states. Instead of summation over all possible states, I'm approximating, so that's why it's stochastic, okay? And we're doing gradient descent here because we compute the gradient first, and then we take a negation of that, and we do fraction of steps. So the alpha is the step size. Okay, so we take a fraction of step in the opposite direction of the gradient so that we reach the minimum. Okay, now I can differentiate this. This is easy to differentiate. So my update is going to be Wt plus 1 is equal to Wt plus alpha times plus alpha times V pi of st minus V of st Wt. When I differentiate inside, I'm going to get minus, so that is what became plus in the beginning, and dou by dou W of V of st comma Wt. Is that clear? So I added a 1 by 2 so that the square cancels when I'm differentiating. Okay, so it doesn't really matter. Now, okay. let's take this equation, okay, and there are few things to observe here, okay. So first of all, this is stochastic. This is a stochastic algorithm because we use only one example instead of one state instead of all possible states, right? And also, if you think about why I started with stochastic algorithm like this, right? Like, so our goal is really not to get zero error for this particular state, right? Because we know that if you get zero error for one state, then you're changing too much for other states because the weights are shared, right? So you're going to affect the error for other states. Then you try to make it zero error for another state, that is going to affect all other states again, right? Like, so our goal here is really not to get zero error, but our goal is to move towards the zero error little bit for all the states, right? So that is why it is very important that we take a fraction of step. You take a fraction of step towards like whatever is the right value function for this state, and you similarly do that for all the states. So on an average, your error is going to go down. Is that clear? Now, the final question is, how am I going to implement this? I don't have access to V pi of st, right? So this is where which family of algorithm you're using comes into picture. So now one can think about function approximation with Monte Carlo, or function approximation with TD, or function approximation with value iteration. Okay. Now, depending on which algorithm you are going to use as the base algorithm, so it is going to tell you estimate for this V pi of st. Okay. So moving forward, we will not call this as V pi of st. We are going to call this as some estimate. Okay. So I'm going to rewrite this equation as Wt plus 1 is equal to Wt plus alpha times Ut minus V of st Wt dou by dou W of V of st Wt. Okay, so where Ut is actually the estimate of the value function. Now, if this is an unbiased estimate, okay, if Ut is unbiased, okay, so then we are guaranteed to converge to the local optimum. Okay, now can you tell me an example for unbiased estimate for value function?
Monte Carlo methods.
Monte Carlo. So what about TD?
Not because we have a bias.
What is the bias in TD?
Value estimates are the bias.
Yeah, so Monte Carlo is a good example for unbiased estimate, right? Because in Monte Carlo, we are the expected value. So when I say something is unbiased, it just means that the expected value of that estimate is going to be V pi of st, right? In the case of Monte Carlo, my Ut is equal to GT. So by definition, the expected value of GT is my value of the state, right? However, that is not true for TD. Okay, so TD is not an unbiased estimator. Okay, now for an unbiased estimator like Monte Carlo, we are guaranteed to converge to the local optimum. Well, in this case, it is a linear model, so we will converge to a global optimum. Okay, now let us see our first algorithm with function approximation. Okay, so this is gradient Monte Carlo for estimating Z. Okay, so remember we are still in the prediction problem. We are not doing control yet, right? So this is gradient Monte Carlo where you have been given a policy and you want to estimate the value of the policy. Okay, now the value function is a differentiable function. In our case, this is basically what? W transpose X of S, right? And you have been given some alpha. Okay, now you randomly initialize your value function. Now you're going to generate an episode, and for each step in the episode, you're going to update your W. Is that clear? Very simple, like you can take your original Monte Carlo algorithm, like, and just do some modifications. You're going to get Monte Carlo with function approximation. Okay, and this algorithm is guaranteed to converge to the local optimum, but in this case, it is also the global optimum, provided like you have certain characteristics of alpha respected, right? Like, so alpha should have, if you remember from our bandit case, like, so the alpha should be in such a way that like it is converging, right? Like, so we are not going to talk about the theory of convergence here, but just know that there are certain conditions that alpha should follow. Is that clear?
Sorry.
Yeah.
GT looks like an algorithm that means we do have access to GT.
GT we have access, right? GT is just the sample return. Yeah.
But then, like with Monte Carlo, also like targets are not stationary, right? So because like GT will be different for every episode.
Okay, so that's a good question. So if you have a deterministic stationary environment, then probably that it is not. But okay, if you have a deterministic environment, then probably it's not very much non-stationary. But if you have stochastic environment, like where the reward distribution is stochastic, then it is non-stationary, right? Like, because sometimes you see some sampled value for the return, sometimes you see some other sampled value. Oh, and also, okay, even in deterministic environment, this is going to be non-stationary. Okay, why? Can somebody explain? So even in a completely deterministic environment, GT is going to be non-stationary. Yeah.
You can have a different trajectory.
Yeah, because you have different trajectories, right? Like the return is computed based on not just this state, like it's based on all the future states and action that you're taking. So if you are taking different actions in different trajectories, then your returns are going to be different, right? Like, so there is always some non-stationarity. So well, probably that would correct my explanation to you during the break. Okay, so
you said it was a deterministic policy. I mean, we are predicting the policies.
yes, but if the policy is stochastic,
Okay. That's only for stochastic.
yeah. Well, the simplest case is you have a deterministic environment with deterministic non-stochastic policy. Okay, so then every time you see the same trajectory, like the trajectory doesn't change then, right? Like then there's no non-stationarity. But that is the least interesting case, like so.
I'm sorry, but trajectory, you mean the X?
Yes. Okay, so now let's talk about how to do function approximation with something like TD. Okay, now we don't have similar guarantees like how gradient Monte Carlo will converge to the optimum for bootstrapping based methods. Okay, so if you think about bootstrapping methods like n-step TD, okay, so in the case of n-step return or n-step TD, like you have G from T to T plus N, right? Even if you consider methods like DP, where your target is summation over all possible A S dash R, phi of A given ST, probability of S dash R given ST A, R plus gamma times V of S dash given WT, right? So you take any of these bootstrapping based approaches, okay? Now you will not have the same convergence guarantees, okay? So it is mainly because your targets are also function of WT, okay? Now let's take simple TD as an example, one-step TD. Okay, in one-step TD, my target is RT plus 1 plus gamma times V of ST plus 1 given W, right? Now when I compute the error, my error for the function approximator is going to be RT plus 1 plus gamma times V of ST plus 1 comma W. This is my target minus V of ST given W, the whole square, right? So this is my error for the function approximator, right? Now, when I compute gradient with respect to this particular error, if I compute dou error by dou w, okay, so there is a problem here, right? Like, so the problem is you see w in both the target as well as the estimator that you are estimating, right? So like you see w in two places. Now, when you compute gradient with respect to w, you have to compute the gradient with respect to 2, like if you want to have true gradient, okay? Now, when you use such true gradients, you will not converge because there's a lot of things happening here, okay? So often, the most practical version of the algorithm is to just consider this as a constant and compute gradient only with respect to this, okay? So it is not a true gradient anymore because we are computing gradient only with respect to the model, not with respect to the target, okay? But you have to do this like if you want a reasonably converging algorithm. Now, this kind of gradients, like which is only gradient with respect to part of the equation, right? Like, so we are going to call this a semi-gradient, okay? So for function approximation with TD, we are going to use semi-gradients instead of true gradients. Is that clear? Now, yeah?
You have convergence guarantee if you treat that as constant, or you still don't have it?
Okay, I'll come to that. So now, for this kind of semi-gradient approach, you have convergence guarantees just for linear case, okay? You don't have convergence guarantees for nonlinear case, like or most of the other cases, okay? Now, in general, well, probably I wanted to talk about it a bit later, but like maybe I'll tell this now. So the moment you start using function approximation, okay, most of your convergence guarantees would break. Now, there are two classes of function approximators, linear function approximation and nonlinear function approximation, okay? When you're in the nonlinear regime, convergence properties for all these algorithms is still an open question. Like there is a lot of active research going on in proving that these algorithms would converge in nonlinear setting, okay? But there has been a lot of work in the last couple of decades in linear setting, like so for most of the algorithms that we are seeing today, like so convergence has been proved, like because we are going to see very simple linear models today, okay? So when we talk about algorithms where there is no convergence guarantee, like I will mention that. Like probably I can give you one example here. No, not right now. I'll come to that, okay? But for now, when you do the semi-gradient approach with linear models, it will converge. Now, what is the solution that it is going to converge? I'll come to that, okay? So that's going to be different than what the solution gradient methods will converge, okay? So we'll come to that. Now, let us see an example for semi-gradient approach. So here you have semi-gradient TD, one-step TD, okay? So this is going to look very similar to gradient Monte Carlo, except for one difference. So the difference is instead of waiting for GT, like you are essentially computing your target. You're computing your target based on the TD update, okay? You can see that in the TD update, this is the target, okay? Instead of taking gradient with respect to both S dash and S, I'm taking gradient only with respect to S. Is that clear? Any questions? So we will talk about like the implications of this semi-gradient approach very shortly. But before that, any questions? Any questions in the chat?
The W equal to 0 means like the full vector is 0 or?
Yes. Oh, that is just an example. Like you can initialize your W to, well, I don't know why.
Treat all features.
Yeah, I don't know why the book suggests W is equal to 0 as a good default initialization. Default initialization as W is equal to 0 is bad. So maybe it's okay for linear methods, but definitely not okay for non-linear methods. So a good general strategy is to initialize W to some small non-zero values. Okay, so you would often do like a Gaussian distribution with 0 mean and 0.1 standard deviation so that everything is very close to 0 and you start from there. Okay, so for linear setting, this is okay, like W is equal to 0, but we will see next week that it is actually a bad initialization for nonlinear methods. Okay, so now let us actually see a simple example before we continue. Okay, so the example, so there is something in between these two extremes. Okay, in one extreme we have tabular approaches where there is no sharing of knowledge between the states, like you only have estimates of these states independently, right? But in the other extreme you have function approximation, right? So where there is a complete knowledge sharing among the states. You update one state, all the states gets updated. Okay. Now we can actually do something simpler. Okay, the simpler strategy is what is known as state aggregation algorithm. Okay. Now the state aggregation is actually the simplest form of function approximation, where the idea is, given a bunch of states, I'm going to group these states into multiple groups. Okay. And I'm going to estimate only one value for this entire group of states. Is that clear? It's really simple. Like you have 100 states, you group it into, let's say, 10 groups. So you have only 10 super states now. Okay. Now you're estimating the values of these 10 super states. And every time you want to know the value of one particular state, just check which super state it belongs to, that is the value. Now you can see that this is like a crude approximation of like the value. We are doing this so that we can scale up instead of like considering each state specifically, right? Like so. Now, if you think about it, like when you aggregate, let's say this is my state space, and I'm aggregating it into multiple groups, right? Now you generalize within the group. Like for example, let's say there are 10 states here. You see only 4 states. You are generalizing to the remaining 6 states by grouping them together, right? So now there are many practical questions here, like for example, how do I group states? So this is where I think there was one of the solution method that you proposed, right? Like so, like imagine you have a similarity function, which tells you like how similar is given state to a bunch of representative states, right? You can start with a bunch of representative state, and any state which looks similar, you put it in that bin, right? So you can develop a practical algorithm using this, but we are not going to talk about that much today. But one way to think about the reason why I'm introducing state aggregation after function approximation is because now you can see that state aggregation is really a special case of function approximation. Now imagine there are 10 features that you have in your function approximation, x1 of s to x10 of s. Okay, and each feature is going to be corresponding to one group of state. So feature 1 is going to be 1 only for this state, and the rest of the features are 0. Then when you're in this group, the second feature is going to be 1 and the rest are 0. Okay, so now you can do gradient method or semi-gradient method. You will just update. So essentially when you're doing gradient method here, the gradient for this particular state when you are seeing something from this state is going to be 1, and the rest of the states are going to have 0 gradient, and so on. Is that clear? So now let us see how this kind of method would work. Okay, so here is an example. Like we are going to look at 1,000 state random walk. Okay, so if you remember the random walk MDP that we have seen before, like I think we saw a 19 state MDP, right? So you start with a middle state, and then you move to one of the 2 states, right? Like so, for example, like you move all the way to okay. So you have this. You start with the middle state. This will be the 500th state. Okay, and you can go all the way left or all the way right. If you go all the way left, let's say you get a reward of -1. You go all the way right, you get a reward of +1. Okay, and the rest of the states will have 0 for transition. Okay. Now, in this setting, right? Like, so for this particular like 1000 state problem, like, so I think there are some other details here. Like, so for example, from what, like in terms of the policy, so the kind of policy that we are going to consider is like, given a state with equal probability, like you will move to either the left 100 neighbors or right 100 neighbors. Okay. So which means you can move from 500 to either 499 or 497 or 490. Okay. So like with equal probability, like 100 states in the left, 100 states in the right. So of course, when you go close to the corner, you put more probability for going right because some states are missing. Okay. Now, let's say I want to do state aggregation here. So I'm going to aggregate these as, I think, 10. Okay. So I'm going to aggregate these as 10 different groups. Okay. So state 1 to 100 as one group, 100 to 200 as second group, and so on. Okay. I do state aggregation and I'm learning gradient Monte Carlo. Okay. So you can see the graph here. So the red line that you're seeing, right? That is the true value of these states. Okay. You can see that you have a value of 0 for the 500 state because you can either go all the way left and get a -1 or go all the way 1 and get a reward of +1, right? So the value of the middle state is 0 and the value of the right state goes towards 1 and the value of the left state goes towards -1. Okay. So that is what you want to estimate. Now, when you do state aggregation, then you're essentially learning one value for 100 states, right? So you get this staircase effect, right? Like, so all the states have this value. All the states have this value. Okay. Now you can see that as you do Monte Carlo approach, this is the kind of value function that you will learn. So now in the bottom, I have given you the state distribution mu. Okay. So this is based, now I can construct mu here because it's a very simple task. Okay. So you can see that you visit the middle state, of course, more often because that is where you start, right? So the frequency of visiting the middle state is like, this is so high. So it's 1.3%. Okay. And the rest of the percentage is given to all the other states. And there is more chance for visiting these states when compared to these states. Right? Now you can see that the Monte Carlo estimates that we have, they're kind of influenced by the state distribution. Okay. Now, if you think about the left half, right? So all the estimates that you're getting are kind of tilted up. So for example, like in the first aggregate, right? Like you have state 1 to state 100. Now this estimate is going to be very close to the estimate of state 100 than state 1. Because you see that the frequency of state 100 is high, right? Similarly, here the estimates are going to be more towards the lower state in the aggregate. Like, so for example, you take state 900 to 1000. So 1000 is like least frequent, right? So the estimates are going to be a little bit higher because they are more for state. So they're going to be a little bit lower. The estimates are going to be lower because of the frequency. Okay. So this is just to show how the visitation frequency actually affects your estimates. Is that clear? Any questions about state aggregation? Yeah.
How do you know the state distribution? How? It's just by using a random policy to visit it.
Okay, so in this case, like we have the policy, so we can construct. This is a very simple problem where you can compute these probabilities. So, any questions? Okay, so now maybe let's go back to our discussion on linear methods for functional approximation. Okay, so I will recap what we have seen. So in the case of linear methods, we have x of s, which is basically x1 of s, x2 of s to xd of s. Okay, and my value function is given by w transpose x of s, or summation I is equal to 1 to d wi xi of s. Right? Now in this case, my gradient is going to be really simple. So can someone tell me what is dou by dou w of the value function?
Sum of xi.
Sorry?
The sum of xi.
Yeah, maybe it's easier if you use this equation.
Xs.
X of s, right? It's just x of s. So my update, my SGD update is going to be something like this. Wt plus 1 is equal to Wt plus alpha times ut minus v of st given Wt x of st. Fine. Now this is a linear case, like this is a linear method. So any method that converges to the local optimum is guaranteed to converge to the global optimum. So if you are using gradient Monte Carlo, for example, then as long as you reduce the alpha over time, you are going to converge to the global optimum. Is that clear? Now, what about something like semi-gradient, right? There was this question like whether semi-gradient TD would converge, right? So now, as I mentioned before, in the case of linear function approximation, it would converge, okay? But the solution that it is going to converge is going to be different from the solution that Monte Carlo gradient would converge, okay? Now, first let's try to understand what this new solution is, okay? So then we will see how to make use of this information, okay? Now, first of all, let us maybe consider the continuing case, which is where TD is more useful, right? Like, so there is no episodes, like, so it's a continuing case, okay? Now, if you look at the update equation, it is going to look something like this. Wt plus 1 is equal to Wt plus alpha times Rt plus 1 plus gamma times the value of the next state. I'm going to call this as Wt transpose xt plus 1, okay? I'm just mentioning x of s as x here, minus Wt transpose of xt, the whole multiplied by xt. Is that right? It is just linear function approximation with the TD. Okay. Now, I can rewrite this as Wt plus alpha times. Okay. I can just bring the xt inside. So this becomes Rt plus 1 of xt minus xt of xt minus gamma of xt plus 1 transpose Wt. Okay. So I have just done some restructuring here. Like, so I wanted to bring Wt separately. So these two things have Wt. So I brought xt in and I brought like Wt out. Is that clear? So now, let's say that I keep learning in this continuing task, okay? So once I reach a steady state, okay, for any given W, then the expected weight update, expected value Wt plus 1 given Wt is going to look something like this. It's going to be Wt plus alpha times, I'm going to call this as B and this as A, okay? Alpha times B minus AWT. Is that clear? Where B is nothing but expected value of RT plus 1xt. Okay, so this is a d-dimensional vector. And similarly, A is a matrix. So this matrix is expected value of xt minus gamma of xt plus 1 transpose, which belongs to R d cross d. Is that clear? Okay. Now, let us say this algorithm converges. So what does that mean? So what does it mean in terms of this equation? So when would you say that this algorithm has converged? Yeah, maybe someone else. So anybody who hasn't answered so far, or maybe people in Zoom. So when would you say that this algorithm has converged? Yeah?
When you have solved the linear equation, right? V equals A over WT.
Solve the linear equation. Okay, but what would, we are doing gradient descent here. Okay, so we are not solving the equations. Like, so I keep updating W. When would I say that this algorithm has converged?
When there's no more change in the
When there's no more changes, right? So, or in other words, when I do this equation again and again and again, this expected update, I will reach a point where WT is equal to WT plus 1. So that will happen only when this second term, right? This term goes to 0, right? So now I can actually, if this algorithm converges, I can actually easily compute where this is going to converge. Okay, so let us write that first. So when this algorithm converges at convergence, okay, let us say it converges to some W, which is WTD. Okay, we know that B minus A WTD is going to be equal to 0, right? Which means B is equal to A WTD, and WTD is going to be A inverse of B. Okay, so this solution, right? So we have a closed form solution now. So this is the TD fixed point. Okay, so your linear semi-gradient TD will converge to this fixed point. Is that clear? Now, first of all, I haven't proved that it is going to converge. Okay, so the argument that I'm making here is like, if it is converging, this is what it is going to converge. Okay, now the book actually has the proof of convergence for linear 3D, like, but as I mentioned before, like, we will not focus on proof of convergence in this course. Like, if you are curious about the proof of convergence, it's a very simple proof. You can go and read the proof in the book. Okay, but the good news is this algorithm will converge. Okay, if we trust that, then this is what the solution of this algorithm is. Is that clear? Now, this solution is actually different from the solution that you will get for gradient Monte Carlo, or the solution that you would get for the true value error. Okay, then the obvious next question is, how bad is this solution, right? Because we care about minimizing VE bar. This is a different solution. Now, how bad is this solution, or how close is this to the true solution, right? So again, I'm not going to prove this, but it has been proven that the VE of WTD, right, is less than or equal to 1 by 1 minus gamma of min WED. So the solution that you are going to get is going to be 1 by 1 over gamma times close to the true solution. Okay. Now it looks like it is very close, but it is not very close. Why? Because if you have done your assignment, like, you know that for most of the practical problems, we will set gamma close to 0.9 or 0.99. Okay. So this solution is actually very much off from the true solution. Okay. But again, there are two things to note here. First of all, it's okay, because we know we are already not sure whether this is the right solution, right? So this is just an approximation for value function estimation. Like, it is not anyway representative of our final goal. So probably it's kind of okay. And second of all, there is a small catch with all these convergence proofs. Okay, so most of these convergence are asymptotic convergence, or in other words, you run gradient Monte Carlo for infinite amount of time, then you converge to this solution. But in practice, are you going to converge to this solution? We don't know, right? So on the other hand, we know that TD is extremely faster in Monte Carlo. So even though it is converging to a bad solution, let's not call it a bad solution, even though it's converging to a different solution, it is still going to learn faster and still going to have advantage over Monte Carlo, gradient Monte Carlo. Yeah, question? Yeah, anything? Any questions so far? Okay, so probably we should stop here for break. Well, I wanted to do one more algorithm, but we'll do it after the break. So we'll take a 10-minute break and we start at 11:32. So 11:32.